Welcome guys. You are watching DSA Logic, your one-step solution for data structures and algorithms. I am Sheetal Chandra Nayak, a senior software engineer at Walmart Global Tech. Binary search. Binary search uses the same idea which we use while searching words from the dictionary. This is a very powerful algorithm, but this algorithm only works on sorted data. So either the data is already sorted, or if you have to do multiple searches on the same data, then first sort the data, then use this algorithm. Let's see how this works on arrays. Let's create an array from 1 to 7. And let's say we want to search for the element 5. We need the left element, which is 1, and the right element, which is 7. By using these two, we can find the middle element, which is 4, which is actually less than the search element. So we will discard the left side and use the right side only. In the right side, now left element is 5 and the right element is 7. Middle element is 6, which is actually greater than the search element. So this time we'll discard the right side and only use the left side. So we are remaining only with 5. So as only one element, so left and right both are the same thing. And even the middle element is also same. And middle element is equal to search element also. So you can say we have found our solution. To code binary search, what we need is a sorted array, element which we want to search, and a binary search method. Now, this binary search method is taking the array as the input, the search element, and it is returning int value, which will be the index of that element. So, in this particular case, we want to search for 9, and 9 is at 0, 1, 2, 3, 4, 5. So, it is at the 5th index. Now, so this should return 5. In a binary search method, what we do is we take the left, the right, find the mid, compare it with the search element, and do the process again and again till we find our solution. So for this, what we'll need is a left index, let's call it left, which will be equal to 0 at the beginning, a right, which will be equal to arr dot length minus 1, and mid. Let's not worry about mid for now. As we are going to do the steps repeatedly till we find our solution, we will use while loop. Let's not worry about the condition for now. Let's try to find the mid element first. Mid index equal to left plus right minus left divided by 2. This will find the mid index. We can also do left plus right in a bracket divided by 2. But sometimes this value goes bigger than the int value, and we get some unexpected solutions. So I prefer this one, and I will suggest to use this way. Now we have our mid index. Let's compare it to check if this is equal to our search element or not. To do that, we need a if condition. If element equal to arr of mid. If this is the case, we already got our solution, so we can return the value, return mid. Now if this is not the condition, then we have to either discard the left side of the array or the right side of the array, depending upon some conditions. Those conditions are like this: else if element greater than arr of mid, and else it will be opposite. It will be element will be smaller than arr of mid. Now, when I say element is greater than error of mid, in that case, let's take a look here. So here the mid element is 5 at the first iteration, and that time we are searching for 9. So 9 is the element and error of mid is 5. So 9 is greater than error of mid. So we can say like our result resides in this particular area and we can safely discard this much area. So now we will be searching only in this particular portion. So right remains the same, only the left value will change. So we can say left equal to mid plus 1 and just the opposite in the else condition. Right equal to mid minus 1. Now while doing this, there can be one more condition when we might never find the solution. In that particular case, we can return minus 1. Now it's time to worry about the while condition, and so here we are finding the mid element and then we are searching either in the left side or in the right side. So in our case we are searching the right side here, then we will find the mid element here and done. But there might be a possibility like we are looking for 7 and that time we reach here and left and right are both at the same position and middle is also at the same position like in our introduction video. So we can see this while condition should be like something like this: left less than equal to right. So here what we are saying is we are going to do this repeatedly either till we find our solution or till when left is less than or equal to right, because because of this sometimes left will be greater than right and then we don't need to process further, we can safely return minus 1. We can say we didn't find the solution. Now it's time to test it out. So we can see we got the solution as 5, which was expected. So our binary search is working correctly. Let's try with some more inputs. Let's search for 2, let's search for 14, and let's search for 3. So when we are searching for 2, this output should be 1. When we are searching for 14, it should be 6. And when we are searching for 3, it should be 2. Let's test it out. Okay, so we can see 5, 1, 6, 2, which is as we expected. So our binary search is working very well. Now let's see how it is better than a linear search. Let's try to put some loggers and see how many steps it is doing. So whatever is inside this while loop, let's call it a one step. So let's put a s out here and this will print something count. And let's take a count. Let's do count plus plus every time. Int equal to 0. Now we are going to search for the same 9 element, and if it would be a linear search, it would have taken 5 steps to find the element 9. But in a binary search, let's see how many steps it takes to find the solution. So as we can see, it only took 2 steps, the step 0 and step 1, to find the solution. Let's try our binary search on a bigger size of input. Let's create an array of 100 elements. We can also create it like this: in string, range closed, 1 and 100. Convert it to array and done. Let's change the element also. Let's say we want to search the element 98. Let's run and see how many steps our binary search is going to take to find the element 98 in an array from 1 to 100. We can see it only took 7 steps to find the element, and it is written in the index also correctly. If it was a linear search, it would have taken 98 steps. So that's the power of binary search. Let's try it out with 1000 elements also. I'm just increasing the size to 1000 and the element to 998. And let's see. As we can see, it only took 10 steps to find the element 998 and the index is 997, which is absolutely correct. Now, we observed like when it was 100 elements, it only took 6 steps. When it is 1000 element, it only took 10 steps. Now, when it was only 7 elements, it only took 2 steps. So we can see like the array input is increasing drastically, but the number of steps are not increasing drastically. It's increasing very slowly. So these kind of algorithms are called to have time complexity of log n. So log n is the time complexity where the input increases heavily, but the number of steps increases very slowly in compared to the number of inputs. So that's the binary search for you. We also have a recursive version, but that we will see when we learn about recursion. Hope you liked it. If you liked it, please like, share, and subscribe. Thank you so much.